Hello guys, good evening.
Good evening, sir.
So what is happening? What about your school exam? Like unit test and all?
They told they'll conduct it.
When? What?
They told they'll conduct it, but we're not sure when.
Okay, so not sure, right? So you did not have any one of your unit test this year, this session, correct? 12th class.
No.
You'll get marks. Okay, few minutes we'll start. So last class we were discussing about what? Grignard reagent, right?
Yes, sir.
Okay. So what was the last reaction we did?
Nucleophilic addition elimination.
Okay. Okay, so nucleophilic addition elimination. Did we start this or we have finished it?
We have finished it.
Could you tell me the last reaction we did in this?
6-ring carbon with
The epoxide reaction we did? I got it. The diol formation, no?
Yes.
Right.
Yes.
Fine, I got it. Wait. Just 1 minute, we'll start. Take some water.
Good afternoon, sir.
Okay.
Good afternoon, sir.
Good afternoon.
Good afternoon, sir.
Next, a reaction that is epoxide reaction. See, three main types of reaction we have for Grignard reagent. That is, the first one is acid base, second one is nucleophilic addition, and third one is nucleophilic addition elimination. However, the third one is similar to the first one. Okay. Only one leaving group is present, so that shows elimination also. But the addition of Grignard reagent is nucleophilic way only. Okay. Now all these reactions comes under the nucleophilic tendency of RMGX. Okay. The fourth reaction I write down, epoxide reaction. Means the reaction of epoxide. Okay. Now what is epoxide? Epoxide is a 3-membered ring in which oxygen is present in the ring. Usually it is 3-membered. Okay. 4-membered also possible, but 4-membered ring is, it's more stable than 3-membered, and hence it does not show this reaction. Okay, now you see this is epoxide. Now when this reacts with R minus MgCl plus with H plus H2O. R minus MgCl with H plus H2O. Okay, this R minus, it is behaving as a nucleophile and it attacks on this carbon atom, R minus. Okay, this sigma bond breaks, goes onto this oxygen, and the ring opens up. So what we get here, you see, we get this reaction, O minus, and here R attached with this. Correct, out of the Grignard reagent and this. In the next step, what happens with H plus H2O? H plus H2O, this H plus comes over here and forms R CH2, CH2OH. What we get here? 1 degree alcohol. So all these reactions you see, these reactions are the reactions of alcohol. Any doubt?
Yes, sir. 1 second, sir.
Okay. Done?
Done, sir.
Okay. Now one observation here, it is what? In epoxide ring, we get alcohol, and the number of carbon atom here in alcohol is 2 carbon more than the number of carbon atom present in the alkyl group of Grignard reagent. So R is the alkyl group of Grignard reagent, and here we have RCH2 CH2OH. So we are getting 2 carbon atom more from the alkyl group of Grignard reagent. Okay, so when you have to increase the carbon chain, then this kind of reaction we can use. Okay, so write down one note here. This reaction is used to increase the carbon chain, by 2 carbon atom. Okay, carbon chain by 2 carbon atom.
So do we have more epoxides that can take place in this reaction?
Just a second, Venkat.
Okay, sir.
Tell me what happened, Venkat?
So can there be more epoxides that take place in the same reaction?
We can
Like
have
you told about
derivative.
4 membered, others?
I'll show you. This
Okay,
is
sir.
was one example we have done. I'll show you the other one. But
Okay,
the
sir.
point is, when you have this, you'll get three, 2 more carbon atom in this. Okay.
Yes, sir.
Plus alcohol we are getting. Okay. This reaction you see, CH3CH derivative here. You see in the first one, what happens? We have equivalent carbon, right? Whether this R minus attacks on this carbon or this carbon, you'll get the same result, right? Same molecule. So there we do not have any confusion, either this one or this one. But here in this case, when the R minus attacks on this carbon or on this carbon, they give different result in both the cases. So which reaction is taking place here? Where the R minus attacks? Okay. R minus MgCl plus and
The
H
second
plus.
place.
Okay. Now here you see this R minus
Center
attacks
carbon.
on the carbon atom which is less hindered. Got it? This carbon atom is less hindered relatively. Okay, less hindered, right? So here the attack won't take place, but this R minus will attack onto this carbon atom. And when it attacks over here, the sigma bond breaks and it goes on this oxygen atom. Understood? So the product is CH3 CH O minus CH2 and R. So with H plus H2O, it converts into CH2R. Understood? So what we are getting here? We are getting 2-degree alcohol here. Now this reaction of R minus, this attack of R minus is SN2 type attack. Write down. Okay, SN2 type, and hence it attacks at less hindered carbon.
But does that mean we'll get primary alcohol as minor product
What? Where?
in this only?
See, we cannot say no for this. Absolute no won't be correct. But yes, the chances are very less. So we can say almost 98-99% of secondary alcohol we get over here.
Oh,
So we
okay,
ignore that possibility actually.
okay. Okay, sir.
Okay. So this is one there. So what we are getting in these two reactions, epoxide and this, we are getting alcohols. Chances are either we get 1 degree alcohol or 2 degree alcohol, depending upon the structure of epoxide. Could you tell me the product here? Did you finish this, all of you?
Yes, sir.
Tell me the product in this one. CH3 MgCl H plus H2O. Write on the product.
Done, sir.
Done?
Yes, sir.
So where this R minus attacks, the nucleophilic attack is
R minus is on the corner of the hexagon.
there here.
Yes, sir. There.
Yes, sir, there.
Or left hand side.
So this attack from this side,
And that epoxide will
goes
open up.
right? Ring opens up, right? So the product here is this. Here what we get? OH.
OH. And next to
And
that
side
H.
CH3 will be here and H will be here. So you see from opposite side this CH3 will come, right? This side. OH and CH3 will be on the opposite side. That's very important.
Why, sir? Like I hadn't written it that way.
SN2, you know, it's SN2, so it comes from the opposite side and goes up. So you see this, you did not pay attention here, I guess. Just a second, I'll show you. You see this? O minus and R on this side, no?
Oh, okay.
Opposite side attack. This side it won't attack, no, because we have this ring this side. So it comes from the opposite side, rings open up and we'll get this. Fine, understood?
Yeah, understood, sir.
So this CS3 will be on the opposite side, OH will on this side, right? Now this can also attack onto this carbon, equal probability, correct?
Yeah.
These two carbons are equivalent carbon, right? So the chances for this R minus to attack on this carbon, and here we have equal probability, correct? So we can also write one of the mirror image of this as the another product. Okay, so that would be this. The mirror image of this is CS3 on the top here, H, OH and H. Okay, so these are what? These are enantiomers.
They cannot be able to superimpose.
The mixture is what? The mixture is optically inactive.
Inactive, equal percentage.
Yes.
Racemic.
Done?
Yeah, yes, sir, done.
Okay. Next reaction, write down the reaction with cyanide, fifth one. So the reaction is, we have suppose RMgCl, Grignard reagent, reacts with cyanide, that is RCN, and it converts into first A, and then with H plus H2O, it converts into B. So what is this A and B? Okay, so the answer for this one, the product A is okay, we'll see the mechanism for this one. You see R minus and this is R1CN. So the Grignard reagent R minus, I'll write down RMgCl only, R minus plus R1C triple bond N. This R minus attacks onto this carbon atom because again this carbon is what? It is polar.
HP.
And pi
Three
electron
bonds.
comes onto this R1C double bond N R. Okay, here we get N minus because pi electrons comes over here, and to neutralize this we can write Mg plus Cl.
Sir, what's this reaction called then?
This there's no name reaction. It's a reaction of cyanide with Grignard reagent.
Okay, sir.
Okay.
Seems different.
Sorry.
Seems different.
Yes. So the reaction mechanism is a bit different also from others. So with H2O, what happens? You see, what you need to understand here. With H plus H2O, H plus, I forgot to write, it converts into R1 C R double bond NH, and MgCl goes with OH. This forms here. Right, in the next step, with H2O, what happens? This carbon takes more electronegative atom, that is HOH. So what is happening here? You see, this bond you need to break. This bond you need to break. Carbon goes with more electronegative atom, oxygen, nitrogen goes with this. So the next step, the product we have RCOH, single bond NH2, and here we have R1. Again, the same reaction we have with H2O. So again, OH comes onto this carbon and NH3 goes out, this bond breaks. So we get here RCOH, OH, R1 plus NH3 eliminates from this. Copy this down first.
So 1 second, sir. I'm trying to understand.
Done?
1 second, sir.
Done, sir.
So wait, sir, could you repeat the white arrow to red arrow thing?
This one,
Yes, sir.
from here to here.
Yeah.
See, it's a simple thing basically. How to write down the product whenever you have C double bond NH. Okay, H2O you have, so we have HOH bond.
Yes, sir.
So here the lower electronegative element goes with the more electronegative element. Means carbon goes with oxygen, nitrogen goes with hydrogen. So we'll get this. And exactly same thing happens here also in the next step. It is actually, the actual thing is, from this H plus comes onto this nitrogen because nitrogen has lone pair up on it. So it becomes NH2, pi electron shift here, becomes NH2, correct? And here the positive charge takes this OH minus on this.
Okay.
So we get C, OH, then NH2. Next step, the same thing happens with H2O molecule, we'll get this.
Oh,
Correct?
understood, sir.
Okay, so this is the reaction. Now the thing is, what is A in this one? A is this molecule. This particular thing is A, which you won't get as a final product, obviously. They won't ask you what is A we get here, but A is this. After this, the reaction of H plus H2 only, nothing else. Okay. Now, when you get this diol, 2OH on the same carbon atom is not at all stable. I have told you this many times. Okay. So further what happens from this diol, COH, OHR1, from this water molecule eliminates on its own and converts into RC double bond OR1 plus H2O. So we'll get ketone finally, right, by the elimination of water molecule. Okay, so overall, how do we write down the product that you try to understand? Because this mechanism you're not going to write every time in the exam, right? So what was the reaction you see? RMGX, RC triple bond N. Okay, so what happens here with H plus H2O? The final product would be this R group of Grignard reagent, R1 of this cyanide. So R1 connected with this. This is the product we get.
Understood, sir. If you wrote mechanism, it will be too time consuming.
What?
If you wrote mechanism in exam, it will be too time consuming.
That's what, that this and this with some double bond O you need to write. Plus what all things we'll get here? Ammonia molecules eliminates
MgOHCl.
and water also comes out into this reaction.
MgOHCl also.
Done?
Done, sir.
Write down the product in this reaction.
We'll write these with mechanism, sir.
No, no, no.
No, okay.
If you want, you can do it for the first one, but you should understand how to write down the product directly. I suggest for the first one, you write down the mechanism.
Ah, yes, sir.
Done?
First one done, sir. We'll need mechanism and all. Completed, sir.
First one. What is the answer?
CH3, CH2C, phenide, and ketone. Ah, yes, sir.
Sir, first one done, sir.
Yes.
Plus
Plus NH3 and H2O.
MgOHCl.
MgOHCl also we get.
Yes, sir.
What about this one?
Propanol.
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 Yes, sir. Huh? Ah, yes, sir. C2H64.
Why is this reaction?
What, sir?
Why this reaction we have? Why this product?
Because of the exception.
Because this reaction is acid-base reaction. The first type, if you see.
Oof.
correct? R minus takes H plus, acidic hydrogen, this one is, right? But there will be some amount of ketone also, sorry, aldehyde also. That is CH3, CH2, C double bond O, H. So you'll get the mixture of two. Okay. Tell me. C2H6 from the first reaction, the acid base that I have discussed.
Yes, sir.
RMGX with acidic hydrogen, active hydrogen, forms alkane, right?
Yeah.
So it gives alkane plus aldehyde also. Okay. But the amount of alkane will be more. Rate of acid-base reaction is maximum out of the rate that we have discussed. Means the first one is acid-base reaction, then nucleophilic addition or nucleophilic addition elimination. And the last type we have SN2 type reaction, the rate. I'll discuss these things, I'll tell you later. Okay, but in this one, we'll have a small amount of aldehyde plus alkane also forms in this reaction, correct? Okay, next type write down. Sixth, SN2 type reaction of RMGX. SN2 type, okay? Right on, this kind of reaction is possible. This kind of reaction is possible generally with alkyl halide. Okay, generally happens with alkyl halide. You see the reaction here, R minus MgCl plus plus CH3Cl. This attack of alkyl group, this one is SN2 type, and this goes out as a leaving group, and it forms RCH3 plus MgCl2. Okay. In this one, we'll get a transition state, and the transition state is this. Carbon has 3 hydrogen at the corner of a triangle, and this chlorine is about to leave, and this R minus is about to attach. Trigonal bipyramidal transition state forms, and finally this bond forms, this goes out as a leaving group.
Typical SN2.
Done?
Just a section.
So in this also we are getting alkane. So write down priority order of rate of Grignard reaction. Okay. acid-base reaction has the maximum rate. Priority order is this: acid-base, then we can write a nucleophilic addition, or nucleophilic addition elimination, and the last we have SN2 type. This is the priority order we have.
So can a reaction be both acid base and SN2 type
Sorry,
with Grignard reagent?
acid base? No, that's not possible.
Oh, okay, sir. That means it'll be controversial because both will give alkane only.
Sorry, what?
That will be controversial. Both will give alkane only.
Yes, both will give alkane, but here we do not have active hydrogen. The mechanism is different, no?
Yes, sir.
That's why both not possible. Done? Now, based on this priority order, you can find out the the type of reaction first, and then based on that, we can find out the rate of reaction. Okay, so you see these examples, write down the question. Compare the rate of reaction of Grignard reagent. Compare the rate of reaction for Grignard reagent. The first question is CH3Cl. Then we have CH3Br. CH3Br, CH3I. Second one is Cl, CH3, CH2Cl. Try these two first. Done?
Yes, sir.
What is the
All are
answer?
SN2 dates only, right?
Yes.
So first one's 3 to 1.
So first one is I minus is the best leaving group we have. Hence the rate of order is this, reaction is this. Okay, here we have 2 degree halide, 1 degree halide. 1 degree halide shows better SN2. Order is this. Yeah, correct. This is the order. Now, one type of question that they ask here, they ask this question in integer type J advance also. Okay, write down the question. How many moles of Grignard reagent gets consumed for the molecule? and the molecule is this. Here we have chlorine, double bond O, OH, N, in this one. How many moles of Grignard reagent consume in this? All these reactions we have done. Okay, if you want, you can take the reference of your notes. Tell me the answer.
So 1 second. Should we proceed the question in any order, like acid-base nucleophilic and then SN2, or nucleophilic SN2 and then acid-base, or something like
No,
that?
I just want how many moles of GR gets consumed in this reaction.
Okay.
Means wherever it is possible, we'll consider that.
Okay.
See here what happens.
3.
First of all, 1 mole consumes over here, yes or no, of Grignard reagent. And what is the reaction we have here? SN2 type, 1 mole, correct? No, that's not correct, Venkat. 1 is what? Here we have 1 mole here, nucleophilic addition, correct? Nucleophilic addition. One more here. Again, what?
Sir, is it 4 moles?
No. Again, it is nucleophilic addition. What about here? How many moles? 1 moles, it is acid base. And here how many moles we consume? 1 mole for nucleophilic addition plus 1 mole for addition elimination. Addition elimination. Here we have nucleophilic addition, and for this one more we have nucleophilic addition elimination. So 1, 2, 3, 4 plus 2, total 6 moles gets consumed.
So,
Right.
so here 1 mole for the keto group and then 1 for the ether.
Yes.
Toxic.
Any doubt in this?
No, sir.
Okay. So this kind of integer type questions you may get in the exam. Okay. 7th reaction. Reaction with halogen. See the reaction, we have RMGX reacts with chlorine, suppose, and it forms RCl plus MgXCl. This is the reaction we have. Simple, delta positive, delta negative. So this R minus attacks on this goes out as a leaving group. This attacks onto this and this goes out as a leaving group. Got it? Answer for this too? It forms RBr. It forms Ri. Okay. This is one type of reaction where we have halogen, right? Similar type of reaction we have with other compounds also. I'll show you how. See, this is A, reaction B, which is similar to the reaction with halogen. Suppose we have RMgCl and this reacts with oxygen, O2. It forms what? H plus H2O also we use here. First of all, it forms RO minus MgCl plus, and then with H plus H2O, it converts into alcohol. Okay, for this reaction, we use 2 moles of this, we get 2 moles of this, and finally 2 moles of alcohol we get.
Yes.
Okay, what is the mechanism of this reaction? You see, we have oxygen O double bond O and R minus. Okay, this R minus, it attacks onto this oxygen and this goes out onto this oxygen. RO, O with lone pair on this oxygen, negative charge. Okay, now the another molecule of this R minus, this also attacks onto this and this goes out here. Means this has, here what happens, this has lone pair repulsion. So it has tendency to break this bond and hence it converts into 2 molecules of RO negative. And then with H plus H2O, we'll get this ROH. We can also explain this with free radical mechanism. But mechanism is not important for this, but it is a bit different type of reaction where RMGX reacts with oxygen in presence of H plus H2O and gives alcohol.
Sir?
Yes.
Sir, here oxygen has minus charge, so what will anion?
Actually, what happens when you heat this, no? This O takes this electron pair, goes out. And that's why this oxygen get attacked by this R minus. So first this bond forms and then this attacks. I have written it in one single step, but it happens this way.
Yes, sir.
Okay. So this gives you 2RO minus. With this we'll get alcohol. So RMGX with oxygen gives alcohol, right? Okay, this reaction, you just memorize it. It's important also. Okay, it's a different kind of mechanism here, right? But important. So must remember this. Now, the next type of reaction you see, we have already seen this reaction when RMgCl reacts with HCl. It forms RH plus Mg CnCl. Okay, but this RMgCl when reacts with ClCN. Okay, so this converts into Cl minus goes out as a leaving group. We'll get cyanide first plus MgCl2, and cyanide goes under acidic hydrolysis, if you do this, if you do acidic hydrolysis further, it converts into ketone. This reaction is exactly similar the way that the reaction we have discussed in reaction of cyanide. Okay, the previous one. Same mechanism we have here. Plus MgOH Cl. R group attached with C double bond O.
Done, sir.
Done?
Yes, sir.
Okay.
Yes, sir.
Now, this reaction you see, organometallic compound. Okay. Organometallic compound, like I told you, it is the compound which has carbon metal bond. Okay. So few information you should have to understand this reaction. Important one, this one is, right. RMGX is also an example of organometallic compound. Compound which has carbon metal bond. Okay, carbon metal bond. Now the metal you see here, the metal we have Li, Mg, metal of S block, then Cu, Zn, Cd, Hg. Okay, so this is the metal we have here. These are strong base. S block metals has a strong base, and these are moderate or weak base, we call it as. Okay, moderate or weak base. Okay, so when the alkyl group forms bond with this metal, like suppose RLi, or suppose we have RHG. Okay, so RLi, because it is a strong base, it has maximum ionic character. Maximum ionic character. And the one which has weak base, it has maximum covalent character. Maximum covalent character. Okay, after this you write down, this kind of compound shows metal exchange reaction okay, this kind of compound shows metal exchange reaction, and the reaction goes towards and the reaction goes towards the weaker base always. Okay, weaker base always. So all these information you should have to understand the reaction. I'll show you some more reactions here. You'll see, suppose I'll write down this reaction RLI. It reacts with, suppose, CdCl2 and it forms R2CD plus LiCl. Okay, now you see this compound RLI, I told you already, it is the strong base, correct? Strong base, and this one is weak. I have given you above. This is weak, this is strong. Okay, one more example, if you see 2RLI plus HgCl2, it converts into R2Hg plus 2LiCl. R2Hg plus 2LiCl. Okay, this reaction also, you see, it is strong and this one is weak. So it is also spontaneous. This is also spontaneous, possible. Okay, but when we yes.
Sir, so if we have R2Hg and LiCl, no reaction possible, right?
The other way, right?
Yes, sir.
No, it's not possible. Like one example I'll show you here. R2CD, suppose, the same thing that you are saying, plus LiCl. This reaction is 2RLi plus CdCl2. This reaction is not possible because weak to strong it is going.
Okay, sir.
Okay. So these are the metal ion, because why we are talking about metal ion, metal carbon bond here, because organometallic compound is RMGX also, right? So the R minus that you are getting in the reaction, it may come from these metal ions also. You can have RLi, you can have RMG, you can have RHG. Okay, so the R minus, the carbon ion group, can come from any one of these metal ion, whether it is strong or weak. So what happens in this reaction? Now this information you have, based on this, you see this reaction. Suppose you have a compound, this double bond O, and when this goes under, reaction with R minus H plus H2. And when this goes under, R minus H plus H2. Now, depending upon the source of this alkyl ion, okay, source of this alkyl ion, it may be weak base, means like R2Hg, R2CD that we have, or this is, suppose we have a strong base coming from the strong base. This is the two possibility we have. Now, when it is a strong base, it gives KCP, right? Kinetically controlled product. When it is weak base, it is TCP.
Thermodynamically controlled.
Thermodynamically controlled product. Okay. So TCB is what? Thermodynamically means we get stable alkene here, more stable product. Stable product, slow forming. Slow forming. KCP is fast forming product. Not much stable, but it is fast forming product. And if you remember, KCP is 1,2 product, addition product. And this is 1,4 addition product. Clear?
So could you please show some examples?
I'll write down the product in this one. Wait.
Yes, sir.
Okay. So 1,2 addition, the addition takes place at first and second position. So first and second position, the product here is one side will get OH, here we'll get R. This double bond will be as it is. Fast forming. 1,2 addition, 1,2 addition. For 1,4 addition, you need to draw the resonating structure of this. And when you draw the resonating structure, you'll get this double bond here, positive charge, single bond, negative charge. Correct? Then R minus attacks onto this, forms R O minus with H plus H2, it forms what?
R OH there, where O minus is there now.
So we'll get OH here and R, but then after it tautomerize and it converts into this one. Copy this.
1 second, sir.
Done.
Done, sir.
Finished?
Done, sir. Yeah.
Yes, sir.
Okay, so this you have to memorize. Whenever you have a strong base, then we'll get fast forming product, not the stable one. 1-2 addition. First and second correlation will do the addition. Okay. When we have weak base, gives TCP 1,4 addition. This is the product. Okay, done. Write down the product in this reaction. Write down the product in this.
So could you explain the mechanism of strong base? Like I can write the product, but
Just a
the
second.
mechanism.
Yeah, tell me.
So could you please explain the mechanism of the strong base reaction? I mean, I can write the product, but I want to know the mechanism, sir.
See, when you have a strong base, then this won't wait for the resonance to take place. Okay, it directly attach onto this carbon, because you see this carbon atom is attached with an electronegative element, correct? So here we have partial positive charge, right? So this positive charge
Yes,
will strongly attract the base over here because it is strong. It can easily attack onto this positive charge ion. But when we have weak base like this, then it requires a fully developed charge on this, like this.
Okay.
It's a weak base, so it requires more positive charge density, fully developed charge. So this will wait for the fully developed charge to develop onto the carbon, which happens after resonance.
Oh, okay, sir.
That's
Okay.
why to draw this structure, the product here, we'll draw the resonating structure of this one and we'll get this. And then this attracts onto this.
Yes, sir. So 1 minute, I'll write this down, please.
But this strong base, if you have, so this won't wait for the positive charge to develop completely. Partially developed charge also attract this base easily. It attracts onto this, pi electron moves onto this, and with H2O, H plus, it gets OH. Understood?
Yes, sir. 1 minute, I'm writing this down. Oh, done, sir.
Finished?
Wrote what you said, sir. So meanwhile, could you go to the next page? I haven't written that question. Answer.
Draw the product in this reaction. Write down the product.
So in the second one, how do we know which thing takes place? I mean, should copper weak base takes place? Oh, nothing. Got it, sir, got it.
Okay.
So what exactly is copper chloride doing here?
What?
What exactly is cuprous chloride doing here, sir? Is it a
See,
catalyst?
this RLI is what?
Strong base.
Strong base. Strong base gives
OH and R side by side.
1,2 addition.
Huh.
1,2 addition is this. It is KCP. Sorry, it is KCP,
Yeah, yes, sir.
OH, and R. 1,2 addition KCP. When you have RLI with CuCl, so this actually reacts with each other.
I knew it. Some trap was here.
Forms R2Cu plus LiCl. Plus LiCl, right? Now this is what? This is a weak base. So weak base gives what? TCP.
Thermodynamically controlled product.
1,4 addition, correct? So hence here the product is directly, if I write down, R comes over here from this group and double bond O. This one is TCP.
So the double bond also will be there in the ring, no, sir?
Double bond O.
Oh, okay. Due to tautomerism, that's removed. Yep, got it, sir. Sir, the copper R2Cu forming is due to displacement reaction, right? That reactivity series we learned in 10th grade. Kanaka by Magalsing and all.
Li displaces copper from this. Okay, so these are the reaction total. I think 8 or 9 type of reaction we have seen for Grignard reagent. Okay, so this is the entire reaction of Grignard reagent, which you must know. Keep in mind, very important reactions these are. Done?
Yes, sir.
Yes.
Next, write down oxidation reduction reaction, the second part of this chapter. Write down oxidation reduction reaction. So we are going to do all types of oxidation reduction reaction there in organic chemistry here in this chapter. Okay. So first reaction you see, the reaction or oxidation of alkene. Alkene, alkyne. The first reaction we have here is ozonolysis. Ozonolysis reaction we have already done.
First formation.
Right? But here we'll see in detail of this reaction mechanism and all. ozone, Zn with H2O. And one more reaction for this we'll see. The first step is ozonolysis, second with H2. Okay. Now the product of this reaction is what? Could you tell me the product? We have done this reaction. Tell me the product.
So just a second, sir.
Aldehyde and ketone.
Aldehyde and ketone. And what is the aldehyde structure here? R1C double bond O H plus O double bond C R2 and R3. If you remember, in ozonolysis, we just break this double bond and place oxygen with this carbon and this carbon, and that is what we did. Remember?
Yes, sir. We form a house.
Okay. Now, in the next reaction you see, which is also ozonolysis reaction, here the product is R1C double bond OH aldehyde plus O double bond C R2 R3. But here, since we do not have zinc, this further oxidizes into acid. Okay. Now you listen to me carefully here. When you use zinc here, right, this reaction we call it as reductive ozonolysis. Reductive ozonolysis with zinc. If you do not use zinc here like in this one, this reaction is oxidative ozonolysis. Oxidative ozonolysis. Okay, and the point you have to memorize here, that in oxidative ozonolysis, we never get aldehyde as the final product, right? In this, aldehyde converts into acid. So ketone forms as it is in oxidative ozonolysis, but aldehyde won't form. Okay, what is reductive ozonolysis? In presence of zinc. When zinc is not present, it is oxidative and it does not give aldehyde as a final product. Copy down this.
So what's the mechanism of the second one?
Copy it down. I'll discuss mechanism.
Oh yes, sir. 1 second. Done, sir.
Done?
Yeah, yes, sir.
Okay. Mechanism of this reaction, you see. Ozone is this. And here we have the positive charge. Okay. If you write down the resonating structure here, it would be O negative charge, and here we have the positive charge. Okay. Now this end you see, this is the electrophilic end of ozone.
Electrophobic end.
Electrophilic end, and this is nucleophilic end. Okay. Now what happens in this, you see, suppose you have an alkene, for example, an oxygen present here, negative and positive charge. Okay. When this negative charge attacks on this pi electrons shift onto this carbon, and this negative charge takes this oxygen. Okay. And this converts into a cyclic ring, which is this. Okay. This compound. This compound we call it as
Ozonide.
is molanoxide. This compound is molanoxide, and this one you see, it is the syn addition. Syn addition. So from same side it is attacking. Okay. Now in the next step, what happens after this? This bond from here, it breaks, it comes over here, forms a double bond, and this comes onto this oxygen. This bond breaks, it forms C double bond O, plus we get carbon O negative, and a positive charge on this carbon atom, because this bond comes over here, so this carbon will have one positive charge. Now in the next step, what happens? This O minus, it attacks onto this carbon, this comes over here, and this further attacks onto this oxygen. So this converts into carbon, one oxygen this side, one carbon this side, with 2 bonds and 2 oxygen attached like this. This compound, we call it as ozonide. In the book, they have given directly this one.
Yes, sir.
Right? Now this ozonide, we know how it goes off. It converts into, with zinc, this comes over here, this comes over here, and this comes out as a nascent oxygen. Right, this comes out as a nascent oxygen, which is nothing but this. We'll get the 2 compound as 2 molecules of C double bond O, plus we'll get a nascent oxygen which has one vacant orbital. Okay, this is a nascent oxygen. Now what happens with this, because we have here, you see, if I go to the previous slide, here we have, because of difference of zinc here, we'll get these 2 products, right? So if zinc there in the last step, it helps in the elimination of that nascent oxygen. What we can say, it extracts that oxygen from that ozonide and forms ZNO.
Zinc oxide, yes, sir.
Zinc oxide. But when zinc is not present, it cannot trap that oxygen, the nascent oxygen, right? And hence that nascent oxygen get attached with this hydrogen over here and forms acid. This comes over here and forms acid. Correct? So this nascent oxygen, zinc can trap, and it eliminates the possibility of formation of acid because the oxygen is taken away. But here zinc is not present, so this aldehyde converts into acid. And that is what the use of zinc we have in the last step. Okay, so this nascent oxygen gets eliminated with zinc and forms ZNO. Got it? This molanoxide, we also call it as initial ozonide.
Not done, sir.
Done?
No, sir. I thought you were going to ask that question. I told it before itself. Say 2 minutes. So could you just repeat that part where zinc is not there? I mean, I understood just like carboxylic last final thing.
Which one? This one? Ye wala?
No, zinc is not there in carboxylic acid forms. Like I understood in
Acid
ozonide and all.
that is coming out, no?
It won't come out.
If zinc is not there, then this will come, but this won't get, see, we have here O minus, correct? So this won't get, trapped by zinc if it is not present. So if you have hydrogen present over here, so this inserts between the hydrogen and oxygen.
Okay.
This,
How is that? Can you show it?
its mechanism is not there. Like if you talk about the mechanism, it's not there. It gets trapped between the carbon and oxygen. So possibly
Okay.
what it comes over here, it get positive charge, right? And we are using water also, correct?
Yes, sir.
So maybe we can say one thing, water attacks onto that carbon, right? Forms H2O plus, and then OH will be there, H plus goes out,
Yes, sir.
correct? So this actually, this oxygen facilitate the nascent oxygen, facilitate the attack of H2O onto this. That
Okay.
is one, this kind of theory written in some book if you see. But the
Okay.
mechanism, the exact mechanism, how this oxygen get trapped between this hydrogen and carbon, it is not given anywhere.
Okay.
That's why I would suggest what? You simply write down this. This is getting trapped between this carbon and hydrogen and converts into acid. Okay. So basically there in this medium, aldehyde won't form. The nascent oxygen, it oxidizes aldehyde into acid. That is also written in some book. Because oxidizing agent, we know aldehyde oxidizes into acid.
Oh yeah.
Correct. So an oxidizing agent provides nascent oxygen in the reaction. One of the way, correct? So since we have nascent oxygen, so this oxidizes aldehyde into acid. That is also you can say.
Oh, okay, sir.
So basically in the last step, you can say the available nascent oxygen we have, hence oxidation of aldehyde, if any present, takes place and converts into acid.
Understood, sir.
Okay.
Yes, sir.
One note you write down. If zinc is not present, then the nascent oxygen oxidizes aldehyde into acid. Oxidizes into acid, and hence it is known as oxidative ozonolysis. Done. So with zinc it is reductive ozonolysis. Without zinc it is oxidative ozonolysis. In oxidative ozonolysis you won't get aldehyde, but you'll get acid and ketone. Got it? Okay, write down the product in all these reactions. Okay, just Advaita, write down. The point I've given is when zinc is not present in the reaction, then the nascent oxygen oxidizes aldehyde into acid. When zinc is not present into the reaction, then the nascent oxygen oxidizes aldehyde into acid, and this is known as oxidative ozonolysis. Done, Advaita?
Yes, sir. Thank you.
Yeah.
So it is actually fun, sir. I like this.
What?
This is fun, sir. It is nice.
Okay.
It's also harmless.
What is the answer first one?
Methanol and propanone.
Okay, finish all four, then we'll start discussing.
Yes, sir. So how can we do ozonide for the molanozonide and ozonide formation, the third one?
That's what you have to do, no?
Ah, yes, sir.
Okay.
Sir, 1 minute, sir. We'll think.
First one you have done, all of you. So write down the product. What you need to do, you just need to break the double bond and attach oxygen with both carbon atoms. So the product is this: double
And
bond
form a house.
O double bond CH2. Okay. Here the product is, one is cyclohexanone and other one is O double bond C HCH3. But since it is oxidative ozonolysis, there is no zinc present here. Then this further oxidizes into acid. Okay. This one is reductive ozonolysis, and the product here is this.
In the other geo.
See, this one is same. You see here the position. The position of double bond carbon is 1, 2, 3, 4, 5, 6. First and sixth carbon, we have double bond present. So double bond O, C double bond O present at first and sixth position only. This is also the same thing. This is just the another way we'll write. 1, 2, 3, 4, 5, and 6. Maximum distance, most stable it is.
Huh. But how do we form that ozonide first in this?
Ozonide
Yeah, yes, sir.
or mono, ozonide forms easy now.
And molonazide. Oh, like inside only the form. Okay. Oh, nice. Nice drawing, sir. Yes.
No one could stop you doing this.
Okay. This is again the Constitution of India. Sir,
What is the last one? See, it is opposite, right? The product is given of ozonolalysis. You need to write down the molecule, the reactant. Done, last one.
just a second.
Yes, sir.
So the answer for this one is what? We remove this oxygen and attach
And
it
just attach those two, yeah.
with a double bond. So this is the answer for this question.
Sir, in the third, sir, no?
Yes.
So the third one, could you show the breaking of the house also?
Breaking of what?
House.
This one.
Yeah.
Done.
Yes, sir. And after that? I'm getting confused here.
After that, nothing. This zinc will take this oxygen. Finished. Here we have double bond O, or here we have double bond O.
Oh, okay.
Okay.
Yes, sir. Sir, it should be in the bridge positions, no, sir?
That's what I said. No. It is the same position only. First and sixth carbon we have double bond. Here also you see first and sixth carbon we have double bond.
Oh, okay. That one you should see.
This way we have the maximum distance, and hence it is a more stable structure. It is actually the same structure, not a different one. First and sixth
Oh,
carbon
okay, sir.
contain double bond. Better way
Okay,
to
sir.
define that. Okay.
Yes, sir. Understood. Thank you, sir.
Write down the structure of A. With O3 ZnH2.
Now, what does water do here? Like I understood ozone, I understood zinc, but what is the water doing here?
Water is a solvent we are using in which the reaction is taking place.
Oh, okay. Thanks, sir.
Tell me the answer.
Hexagon with double bond CH2, double bond CH3 twice. For first one. Yeah. And double bond CH2. Okay, yeah. And double bond CH2. Yes, sir.
Okay.
Correct, sir?
What about this one?
Sir, benzenone.
Sir, benzene with double bonds.
Toluene.
What? Benzene? Sorry.
Not benzene, hexane, cyclohexane with double
Toluene.
bonds.
Is it?
I
See,
guess.
actually, what happens when it goes and first of all, the reaction is oxidative or reductive analysis.
The first one is reductive, second is oxidative.
Oxidative. So when oxidative analysis is there, so obviously one of the product will be cyclohexanone here, and this is we get O double bond C, H first, which further oxidizes into O double bond C, OH and OH. Correct. 2 hydroxy group on the same carbon is not stable. H2O comes out forming CO2.
Understood, sir.
Done?
Yeah, yes, sir.
So can you go to the previous page once? Yes, sir. Thank you, sir.
Product write down. What is the answer? First one.
So dial hexane plus cyclohexane and CHO up and down. Hopefully, right?
Yes.
This is the product we get, correct? This bond you need to break
Yes, sir.
at double bond. Okay. What about this one?
So doing so.
2 molecules of this. Try this one.
Is it trions, huh? Like the actual product?
Actual product is this C3H2O3. The structure
I
is
said don't tell.
see guys here what happens with option, because there are various structure of this is possible. With option you'll get to know that what structure you could think about. Okay, like for example you see this 2 molecules of this we have, and the possible structure is this. Degree of unsaturation, if you find out, it is 3. Hence we have 3 pi bond present into this. So one molecule is this, the another molecule is again this only. These two combines and gives you A, right? This O you remove, oxygen remove, and you remove this oxygen. So the product here, the A molecule is this. This is the structure. Okay, this is the structure of A we have. We can also write down the same structure as this. So with option, you will get to know what is the possible structure here. This is a structure possible. This or this. Both are same thing. Done?
Yes, sir.
Okay. Next, write down the rate of ozonolysis, rate of this kind of reaction, rate of ozonolysis. Write down ozonolysis. We have seen it is a type of electrophilic addition reaction. Write down it is a type of electrophilic addition reaction. Hence, rate is directly proportional to the stability of carbocation. Okay. Now, when you compare for this, which one has the more rate? These three you compare. Okay. Now here you see the carbocation here is more stable. Rate of reaction is this. Here again carbocation, here it is more stable. Rate of reaction is this. Alkene, faster rate of ozonolysis it shows because of sp2 hybridized carbon atom, less electronegative. Alkene shows more rate of ozonolysis. Done?
Yes, sir.
Okay. Now you see ozonolysis on aromatic compounds. So for aromatic compound, what do you have to keep in mind that you try to understand? Okay, aromatic compound first reaction you see, we have this benzene ring. At this compound we have, okay, and this goes under a reductive ozonolysis, Zn with H2O, the product of this. Okay, so here you see, whenever you have a double bond present in the compound, ozonolysis if takes place, right? Ozonolysis it takes place. So it takes place at all the double bond, means here, here, here. You have to break all the double bond and do the ozonolysis reaction. But in case of aromatic compound, what happens? If this double bond takes part in the reaction, the aromaticity will be lost, right? It loses its aromaticity if it takes part in the reaction. Hence, what happens? We have one more possibility for ozonolysis reaction. Hence, the product for this reaction will be, we don't take part ozonolysis. This pi bond won't take part in ozonolysis, and it converts into this plus O double bond C H H.
Sir, I'm not able to see what you're writing.
Sorry? Yeah, tell me.
Sir, I'm not able to see what you've written, sir.
Your fault.
Yeah, but okay.
You rejoin, you disconnect and then rejoin again.
What's that? Now it's lagging.
Okay, so here you see this aromatic ring is not taking part in the reaction. It's not like it won't take part, but the rate of ozonolysis is extremely slow because it is losing its aromaticity. Hence, if you have any possibility to retain its aromaticity in this reaction, we'll retain that. Now, one more example on this, you see. Benzene ring, when it goes under reductive ozonolysis. This is O3H2O. So one is reductive ozonolysis and other one is oxidative ozonolysis. Correct? So here you see, if this double bond takes part in the reaction, then again the aromaticity, it will lose its aromaticity. Correct? But we don't have any choice here. Hence, in this, the reaction takes place for this ring. And the product here is what? You see, we'll get 3 moles of, if you look at the product here, we'll get 3 moles of carbon-carbon bond, double bond O, H, double bond O. Okay, you see, this carbon-carbon, you see, this double bond and this double bond gets break, and same thing happens here also. So this carbon-carbon bond will be as it is, which is here, and each carbon atom we have double bond O this side and double bond O this side, and we get this. So we similarly we get 3 molecules, 1, 2 from here, and third one from this. 3 molecules of this. Tell me.
Hello?
Yes.
Am I audible?
Hello.
Sir, I can't hear you.
Hello. Hello.
I will join again, sir. I can't
Yes,
hear
sir,
you.
we can hear you.
Okay. It's fine.
Yes, sir.
Yes, sir.
Correct. Now, if you have this oxidative ozonolysis, then what happens? And instead of this H, we have what here?
OH.
OH. Everything is same. This is oxalic acid. 3 moles of this we get. This compound is glyoxal. 3 moles of this. both reactions are extremely slow because the compound is losing its aromaticity. So both reactions are extremely slow. Since we do not have any other choice, we have to do this. Here we had this choice, so we did not, consider this reaction over here. Aromaticity retains. Finish?
Yes, sir.
Okay. Now you see the ozonolysis of alkyne, just it is exactly similar to alkene. Just we'll see one or two examples, not more than that.
Sir,
So here the pi bond breaks and it forms this. Sigma bond won't break, it will be as it is. Exactly same. One more reaction we'll see, HC triple bond CCH3, and this is oxidative ozonolysis. This converts into, again this H becomes OH, acid, C double bond O, C double bond O, CH3. Exactly same reaction.
Done.
Okay. Now the next reaction we are going to see, the first three, we are doing the oxidation reaction, correct? First oxidation we have seen of alkene, that is ozonolysis. Now the second reaction we have is hydroxylation. Okay, hydroxylation. Hydroxylation means what? Hydroxylation means addition of hydroxy group. Addition of hydroxy group on both double bonded carbon atom, right? So what happens if you look at this reaction? We have C double bond C, hydroxylation reaction. This hydroxylation reaction is of two types. We can have syn and we can have anti. Syn addition is what? OH OH, syn addition. Okay, anti means both OH on the same side. Write down this.
Done, sir.
Finish.
Yes, sir.
Yes, sir.
So there are few reagents which gives syn addition and few reagents which gives anti addition. Okay. So what are those reagents we'll see. Okay. So write down reagent for syn addition. Reagent for syn addition. The first one is dilute alkaline KMNO4. Dilute alkaline KMNO4. This compound we call it as Bayer's reagent. Bayer's reagent. You see this KMNO4, dilute alkaline KMNO4 means in water, it is of purple color. It shows purple color. Okay, purple color. This is also used as disinfectant. Okay, like KMNO4 is used to clean the wound before dressing. Okay, that is one purpose we use to kill the germs or disease over there. And another thing we nowadays we can also use this because of this this COVID-19 thing. We also use this KMNO4 to clean vegetables and all. Okay, we put this into water, it gives purple color, and then you put vegetables into this for 15-20 minutes, and then you can remove it off and dry. Okay, that is one way some people are using. Okay, because it is used as disinfectant to kill germs and other things. Okay, but that is not the uses over here. We have to understand the reaction of this with alkene. First of all, like I said, in dilute medium it is of purple color. So when you have this alkene, and when you put this into KMNO4, alkaline KMNO4 dilute, the solution becomes colorless. Initially it was purple color, now it becomes colorless. So when it becomes colorless, it's decolorized the solution. So this is the test of unsaturation, test of alkene. Test of alkene or test of unsaturation. Okay, we call it as Bayer's reagent test. Okay, test of alkene, we call it as Bayer's reagent test. Decolorizes the solution. Then, now you see what is the reaction we have here. Nothing much, Venkat. We have just discussed this only.
Oh, okay, sir.
Okay.
Just from aromatic things, sir. Like I'm not sure on that.
What?
From aromatic compounds analysis, I think I missed for 5-7 minutes. I missed it.
You missed from there aromatic compound.
Yes, sir.
Okay, then you just a few things were there. See this, I'll share the video. You can see, I'll just explain a bit here so that you can understand after this what we are going to do. Okay. Aromatic was not the, the major thing. It's just I said that since the aromatic behavior is there, so it has very less tendency to go under ozonolysis reaction. Okay. Here we have chance to react over here. Then we don't allow the reaction to take place over here. Which we don't do, this reaction won't take place at this benzene ring. If it takes place, then it loses its aromaticity. So hence we have the possibility for the reaction to take place at this carbon. So it happens over here. But when we have only benzene ring, then we do not have any other choice. So we have to have this reaction at this particular double bond. So we'll get this compound with reductive, with oxidative, we'll get this compound. Both reactions are extremely slow since it is aromatic compound. Okay,
Yeah,
I'll put the video. Not much we have into this. Now after this, I talked about this alkyne, similar kind of ozonolysis reaction. Second oxidative oxidation reaction we have, that is hydroxylation reaction. Hydroxylation is addition of OH on both sides of double bonded carbon. Okay, so when you have C double bond C goes under syn hydroxylation, gives you this, anti gives you this. Here we are trying to understand that what all reagents gives syn addition, what all reagent gives anti addition.
Correct. Just a second, I'll note down that syn and anti part on this at least. Just a second.
Done?
Just a second, sir. Last. Done, sir. Thank you.
Dilute alkaline KMNO4 Bayer's reagent, purple color, test of alkene, Bayer's reagent test. Okay. So you see what happens in this KMNO4. MnO4 minus. Okay, so the alkene that we have, suppose it is C double bond C, and this MnO4 minus, the structure is this. I'll write down the structure of MnO4 minus here. Okay. Now in this, what happens? This is metal. It can take this electron pair here. So it forms this, you see, one electrophilic end and one nucleophilic end. This is exactly same reaction as we have in ozonolysis. There we have O plus, O minus. Here we have this part. Correct. So now again we have the same kind of reaction here. O minus, O plus, negative charge, double bond O, and here we have the negative charge. I forgot to write. Okay. Now what happens here? This comes here, this comes here, and this takes this oxygen. So this forms carbon-carbon single bond, oxygen, manganese, oxygen, this double bond O, which in the next step, H plus H2O, OH. This is the reaction we have. Hydroxylation reaction. So now you see, since ion is attaching from one side, this side, hence it is syn addition.
One second, sir.
Sir,
Yes. Yes, tell me.
so can you explain the last step once, hydrolysis? So last step, hydrolysis, I didn't understand.
See, it's simple. H plus comes over here, right? And then this bond breaks, we'll get OH here. This also comes over here, this bond breaks, we'll get OH. I forgot to write negative sign. Okay, and then MnO2 goes out from this. OH, MnO2 goes out from this. Got it? This oxygen protonates, no, in presence of acid.
Yes, sir.
Then this
Got it.
over here, and then similar. Okay, mechanism for this is not important. These reactions, mechanism is not important. You just have to keep in mind that these are hydroxylation reaction, and which all reagents give syn addition and anti-addition. Okay, one more reagent we have here which shows syn addition. We'll finish this one and then we'll take a break. Okay, the another one, exactly same mechanism. The second reagent is osmium tetroxide. Osmium tetroxide is OSO4. And the reaction you see both gives, like I said, both give syn addition. The structure of osmium tetroxide is this: OS double bond O, double bond O, double bond O, and double bond O. Okay. In this also, if you draw the resonating structure, this comes over here, this goes over here. So here we get what? Again, you see, we get electrophilic and nucleophilic end. Sorry, plus, negative, double bond O and double bond O. And then if you have an alkene, say this one, we have same kind of reaction. This attach here, this attach here. So I'll write down the reaction directly here. We get with H plus H2O, it converts into C, single bond C, OH, and OH.
So last year we had the same thing just without the mechanism.
Sorry?
Last year we had the same thing with KMnO4 just without the mechanism.
Yes.
NCRT, this reaction.
Actually, mechanism is not required, like I said, for this reaction. But since we are doing it, that's why I have just given 2 lines are there, just I've given this. But
Yes, sir,
mechanism is not at all required. They won't ask you. There is no any possibility of getting different answers if you consider mechanism, like D plus D2 and all. Because you see, here we only get H and H, no? If
Yeah.
there, then we get OT. There's no any difference.
Yeah.
That's why the mechanism based question they don't ask. It is important that when you get syn or anti, that you must keep in mind. Okay, so these two compounds gives you syn addition. We call it as hydroxylation addition reaction. Correct. Fine, guys. We'll take a break now. We'll resume the session at 6:55. Okay.
Okay, sir.
See anti-hydroxylation. Okay, take a break.
Okay, sir.
Hello?
Yes, sir.
Yeah.
Yes, sir.
So we'll get here sin addition, right? Now in this you write down next reagent for anti-hydroxylation. Anti-hydroxylation. The first one, the first reagent we use here is any peroxy acid with H plus H2O. Peroxy with H plus H2O. Generally, we use the peroxy acid, we use MCPBA.
What is that,
Meta
sir?
or benzoic acid. And the structure is this. Metachloro per benzoic acid is this. This is MCPBA. You'll get this only written in the question. MCPBA, metachloro per benzoic acid. Okay. So this we use in the first step, and in the second step, we use, just a second. Okay, fine. So we also use this is one reagent we use, MCPBA in H plus H2O. Another reagent we use, first we'll see the reaction of this and then we'll see the other reagent. Okay, reaction of this you see, if you have any peroxy acid, RC double bond O, OOH, this converts into acid and nascent oxygen, which is RCOOH, and a nascent oxygen we get. This one. Okay, this nascent oxygen reacts with alkene okay, reacts with nascent alkene, and which is this. The lone pair on this bond behaves as a nucleophile, and this comes over here when the pi electrons shift onto this carbon atom. So this converts into an epoxide kind of compound, which is this. Okay, which on acidic medium gets protonates. Here protonation takes place, and this converts into this. After this, what happens? Water behaves as a nucleophile, attacks on one of the carbon atom. This bond goes up, similar to the peroxide, epoxide ring we have, and we get this. So here we get OH, and this water attacked from the opposite side. So OH finally we get here. Understood?
So 1 second, sir, please. Answer.
Okay, this is
Yes, sir.
anti-addition of hydroxy group. The another reagent we use for this purpose, B, write down the next reagent, B. We use silver with O2 in H plus H2. In H plus H2. So what happens here, this Ag plus O2, it gives oxide of silver, that is AgO, and again a nascent oxygen. Nascent oxygen. And for this, again, we have the similar reaction that we have done last time. Okay, with peroxybenzoic acid. Okay, peroxy acid. Right? Same way this reacts. Okay. So you see from questions here, suppose we have an alkene, C double bond C, CH3H, CH3H. When it reacts with any peroxy acid, RC double bond O, OH, in H plus H2O, what is the product we get? The product is anti-addition of OH, and we get this, both OH on the opposite side, H on the opposite side, CH3, CH3.
Understood, sir.
Correct?
Yes, sir.
Okay, so this is the two reagent we have, which gives anti-addition of hydroxy. One is MCPBA, peroxy acid, and other one is silver with oxygen in N plus H2O with this. One more thing you can observe here, we'll get a mirror image of this also. So mixture is what? Racemic mixture.
Racemic optically inactive.
Sorry?
Racemic optically inactive.
Yes, racemic mixture, and this is optically active. The other one is also optically active. Okay. Now the third reaction we have, oxidation of alkene. What all different reagents we have discussed for oxidation of alkene?
Sir, KMNO4 and
Ozonolysis,
osmium tetraoxide.
ozonolysis, then hydroxylation we have discussed. Now
Yeah.
this is the third type. Okay. Don't mix all these. Okay. KMNO4 and osmium tetraoxide is for syn hydroxylation. Peroxy acid, silver oxygen with H plus H2O is anti-hydroxylation. So these four are under hydroxylation. Now the third oxidation of alkene with, write down oxidation of alkene with acidic medium KMNO4, or we can also use acidic medium K2Cr2O7. Now this one, the mechanism is similar to ozonolysis. KMNO4 H plus, acidic medium we have, so it converts into CH3, C double bond OH, plus we'll get O double bond C, OH, OH. Here we get acid. This converts into further CO2 plus H2. This is the reaction we have. So when you have terminal alkene, one of the product will be carbon dioxide. If you remember this one we have discussed, aldehyde won't be the product in this reaction. Write down, aldehyde won't be the product of this reaction. For all these reactions, you need to know how to write down the product. The mechanism is not important. It is not given also in the most of the books. Right, 2-3 points as you write down. Aldehyde won't form in this reaction. We always get acid. Terminal alkene if you have, then one of the product will be carbon dioxide.
Oh, so I didn't understand how to write product also.
Sorry, what?
I haven't understood how to write product.
Why? डबल बॉन्ड ब्रेक कर दो, COH हो गया और यहाँ पे आ जाएगा COH.
Okay, but
See, what I said, aldehyde नहीं form होगा, correct?
yes,
Now,
sir.
when you break this bond, तो क्या हो जाएगा? See this, CH3, C double bond, ठीक है?
Yes,
Now
sir.
we have this hydrogen, but acid forms into this one, so we get OH here. And here what
Okay.
happens? It is similar. O double bond CH2. So we have O double bond C, but again we have H here, so that converts into OH and OH.
OH, okay.
And then H2O comes out, we'll get this.
Yeah, but then, like, should we remember that CO2 is formed?
CO2 forms in case of terminal alkene, otherwise CO2 won't form. You'll get acid.
Okay, it's because of the two hydroxyl groups instability.
Terminal alkene gives you diol, OH. And
It
this
is unstable.
eliminates water and converts into CO2.
Oh, okay. Clear, sir. Thank you.
What?
As writing. I can learn to write it. Done, sir. Thank you. धन्यवाद.
Write down the product in this reaction. Done?
First one done, sir. Benzenone. Ketone and ethanoic acid. Hello?
Yes.
The key. Okay. I just testing, sir.
Acid. Similarly, here also we get okay. Now next write down oxidation of alcohol. Oxidation of alcohol. See, if you have 1 degree alcohol, on mild oxidation gives you aldehyde. Mild oxidation or partial oxidation gives you aldehyde. 1 degree alcohol on strong oxidation or strong oxidation gives you acid. Okay, this is one thing. The second one we have, if we have 2 degree alcohol, on oxidation. On oxidation. Oxidation, whether it is mild or strong, it gives ketone. Okay, this is mild or strong. Gives ketone. 3 degree alcohol, no oxidation. The oxidation is not possible for this. Okay, but when you heat this, 3 degree alcohol goes under elimination, forms alkene and water. Done? Copied?
Yes, sir.
Yes, sir.
Okay. Okay. Now for this purpose, like all these oxidizing agent, the reaction we have, you need to memorize the various oxidizing agent here. There's no other way, right? You need to know what all strong or weak oxidizing agent we have and what reactions gives what product. Okay. So these oxidizing agent, I'm writing it down. You have to memorize this. Write down oxidizing agent. What are the various oxidizing agent we are using? Okay, you must remember all this. Okay, there are few, like I said, strong oxidizing agent. Strong oxidizing agent, and they are KMNO4 in acidic medium, K2Cr2O7 in again acidic medium, chromium oxide with H2SO4, again acidic medium. Okay, so here what happens, you see, in this, manganese is in +7 oxidation state and it converts to MnO2. Okay, purple color, and this is brown. Color you don't have to memorize, but I'm writing it down here. But color thing is not important here. Cr plus we have, it converts into Cr plus 3. This is orange and this is green. Cr plus 6 converts into again Cr plus 3. This is a change in oxidizing agent here. All these are strong oxidizing agent, and this also we use for the test of alcohol. Test of alcohol, 1 degree or 2 degree, because tertiary alcohol does not show this reaction. Okay, 1 degree or 2 degree. With this color change, we can say this. Okay, next to write down mild oxidizing agent. The first one is red hot copper, Cu with in 300 degrees Celsius. If you heat this, this also we call it as red hot copper. Okay, so for example, you see if you have CS3CH2 OH, 1 degree alcohol, if you heat this with copper around 300 degrees Celsius, you see the first page, I have told you that this 1 degree alcohol converts into aldehyde. So this is a reaction we have with equal number of carbon atoms. If you have 2 degree alcohol here, for example, this, with the same reagent, it converts into ketone, which is this. Copy this down. Done?
Yes, sir.
Okay. So another mild oxidizing agent is NBS. It again converts 1 degree alcohol to aldehyde, 2 degree alcohol to ketone. Second one is PCC. It is pyridinium chlorochromate. Pyridine with HCl CrO3. This is the mixture we have. In short, we write it as PCC. You'll get this only in the exam. All these are mild oxidizing agent. PDC next. It is pyridinium dichromate. Dichromate. Pyridinium dichromate is this. Next one is Sarret's reagent. Sarret's reagent is this. pyridine with CrO3 with HCl plus dichloromethane. This is Sarrett's reagent.
Yeah, 1 minute, sir, please. So how exactly do we use these techniques?
Sorry?
How exactly do we use these techniques?
Nothing you have to use, just these are mild oxidizing agent you should know.
Ah,
Okay.
yes, sir. Okay.
So it gives aldehyde with 1 degree alcohol. 2
Oh,
degree
okay. Okay.
alcohol, that is it. Means acid won't form in this reaction with aldehyde, with alcohol.
Okay. 1 second, sir. Aldehyde 1 degree.
I have written this in the beginning.
Oh yeah, even I
Keeping
have written it. I've written it, sir.
1 degree alcohol, mild oxidizing in aldehyde. Strong gives acid. 2 degree alcohol gives ketone. Mild or strong. So you should know what oxidizing agent it is. Mild or strong. That is it.
Yes, sir.
Sleeping.
No, no, no. I've written it, sir. See, blue pen I've written.
Okay. Done.
No, no, Sarrett's reagent, sir. Done, sir.
Okay. The next one is Collins reagent. Collins reagent is this. We have pyridine, 2 moles of this, plus chromic oxide and CH2Cl2. This is Collins reagent. Next one is manganese dioxide, MnO2. This is a special type of oxidizing agent. It oxidizes allylic and or benzylic alcohol. Important this one. For allylic and benzylic, we use MnO2. For example, you see, we have CH2 double bond, CH single bond, CH2OH. With MnO2, it oxidizes this into aldehyde. Single bond C double bond OH. 1 degree alcohol into aldehyde. Benzylic means what? We have benzene ring and on this CH2OH present. So with MnO2, we get benzaldehyde. Very specific oxidizing agent, must remember this. Okay, if you have 2 degree aldehyde, 2 degree alcohol, sorry, CH,
Ketone.
and we have CH3OH. With this, it converts into ketone. See this, it does not affect the double bond. Carbon-carbon double bond, it does not affect. See, it is at allylic position, benzylic position. This is also at allylic position. So for allylic and benzylic alcohol, we use MnO2 for oxidation purpose. Best reagent is this. Done.
Yes, sir.
Try this question. With PCC, MnO2. Write down the product in this.
Sir, I've done it, but I just want one confirmation.
Sorry, what?
I've done it, sir. I just want a confirmation. So, like for example, PCC won't oxidize allylic and benzylic alcohol, and MnO2 won't oxidize the normal alcohols, right?
Correct.
Like they won't perform each other's roles.
Yes.
Okay, done, sir.
Okay, दोनों एक दूसरे का काम नहीं करेगा.
Yes, sir. Okay. My voice is coming muffled, sir, today.
Full.
Seriously, or joking?
Why I would joke?
Okay.
See, PCC won't oxidize allylic alcohol. So it will be as it is. But this can oxidize
Ketone there and
primary and secondary.
aldehyde down.
Secondary into
Ketone there.
and primary into
Aldehyde. Aldehyde.
correct.
And the next one only that
Oxidize
allylic
allylic. So the product here is this.
ketone there, that's it. And copy the rest.
And these two will be as it is. Okay. Okay.
1 second, sir.
Done. See, all these are reactions of alcohol. So after this, we'll be only left with this thing. Only preparation and properties of alcohol. That is it. In fact, properties, these reactions comes under chemical properties only. So mostly we'll be left with preparation of alcohol. Finished?
Yes, sir, understood.
Okay. The next reaction you see, the next one, is opener oxidation. Opener oxidation, 2-degree alcohol to ketone. Okay. Suppose we have this reaction. We use reagent. So this converts this into ketone, which is this. Now, what is the reagent here? The reagent for opener oxidation is aluminium tri-tertiary butoxide with acetone. Okay, this acetone we are using as a solvent here. Okay, tri-tertiary butoxide is what? Aluminium with O whole thrice. This is aluminium tri-tertiary butoxide. Acetone, you know the formula. CS3, C double bond O, CS3. So first step we'll use this, second step we'll use acetone.
So why can't we use PGC? Same thing only we'll get now. Why is this special?
Because it is the name reaction.
That's it.
See, if you ask me why can't, then why we are doing this 7-8 different reagents? There are different reagents, oxidizing agent which oxidizes alcohol. So if you only memorize PCC, then if you get this in the exam, you'll be like, okay, what it is? I don't know.
Okay.
Then you will ask the examiner, why not PCC you have given? Why opener oxidation you have given? Would you get marks in that case?
No, sir. Sorry, sir.
That's why whatever oxidizing agent we have, we can, we should know that what all oxidizing agent we have. Why not here we can use PCC? Yes, PCC if you use it is possible. But opener oxidation is a name reaction. And for name reactions, the various reagents and these things are same.
Okay, yes, sir.
Means you can get this compound with many different methods. No, one of the method is this, which is opener oxidation.
Yes, sir.
So actually you see this compound, it converts into Al3 plus 3O minus and this thing. Dissociates like this. Now for this alcohol that we are using here, since we have 3 ions here, so we also take 3 moles of this alcohol. Okay, so what happens? This is acid and this is base. It takes H plus and forms the anion here. So 3 molecules of this plus. Chalega? Fine. We have hydrogen here. And when this comes over here, this hydrogen goes out and it converts into 3 molecules of what? 3 molecules of acetone. Right. This hydrogen that comes out here, it is taken up by the acetone. That is the purpose we have here. See, the acetone we have here, double bond O. This comes out and this attacks on acetone. So acetone actually helps in the extraction of this hydrogen, hydride ion. And it converts into this. O minus and H here. Okay, so this get reduced, acetone except hydride ion, it gets reduced, and this get oxidized, you get this. Okay, now on this we have one more reaction, which we call it as MPV reduction. Okay, MPV reduction. Write down one note here. This reaction is exactly opposite to MPV reduction reaction. Exactly opposite to MPV reduction reaction. We are doing oxidation here, but let's finish this MPV reduction here only. Okay. So next is MPV reduction reaction. MPV is the letter taken from the name of the scientist. It is Mervyn Pondorf Worley, P-E-R-L-E-Y. Reduction reaction, MPV. Okay, exactly opposite. Okay, so what happens here? We have ketone on reduction gives what? 2 degree alcohol. Exactly opposite. So the reagent we use here for this reaction, the reagents are, we have aluminium H here, thrice. This one, and the another one we use here as 2 degree alcohol as the solvent. In solvent we use the conjugate acid of this one, this part over here. Okay.
Acid as in OH, sir. 2 H is there.
Sorry?
Acid means 2 H there then.
No. Acid means, iska conjugate acid means H plus attached onto this.
Adding H plus. Oh, okay.
Correct.
Okay.
So you see this reaction, AlO whole thrice, it converts into what? Again the same thing. Al3 plus 3 O minus. Okay. Next, what happens here, you see? This exactly opposite of the previous reaction. You see hydrogen we have here, plus it reacts with, suppose ketone is this I'm taking. So this forms pi bond, this comes out and it attacks onto this carbonyl carbon. So we get what here? We get acetone plus 3 moles of this. 3, this is also 3, this is also 3, and 3 moles of this HO minus, and this goes up. Okay, now after this, the solvent that we have, which is this one, OH, this takes this hydrogen from here and converts into 2 degree alcohol, 3 molecules of this, 3 molecules of this, and we get 3 molecules of O minus this, which combines with Al3 plus and forms this one.
So 1 second, sir. I think I'm getting a bit confused here.
Your voice is breaking.
So 1 second, sir. I think I'm getting a bit confused here. 1 second.
Over.
100 minutes, sir.
What?
Nothing, sir. Joke. I made a joke.
I didn't get you.
Which is okay.
Sometimes your voice is like it seems like your voice is coming from too far.
Achha, oh, okay. Now
It's better.
I put my mouth near the
Connect
laptop speaker.
from your side.
Yes, sir. I will do that today. So 1 second, sir. I'll try to process this. Sir, could you explain this white yellow part?
What white yellow part? It is exactly same like the way we have done the previous reaction. See, the reagent we have this compound, right? It dissociates, forms Al3 plus and this.
Yeah.
This then reacts with ketone this way.
Okay.
This lone pair forms pi bond, releases hydride ion, and this hydride ion reacts onto this, attacks onto this. This goes up, we'll get this.
Okay.
Now this is the base we have. It takes H plus from this solvent.
Okay.
Forms it. That is it. This converts into ketone, converts into alcohol.
Yes, sir. Wait,
Write down
1 second.
step by step, you'll get it.
Okay, sir. Where does that hydrogen go?
Which hydrogen? Hydrogen है यहाँ पे. I won't write hydrogen also, no?
Oh, okay. I am very intelligent.
Sleeping.
No, no, sir. Understood, sir.
Okay.
Yes, sir. Thank you.
All these reactions are for alcohols. You see, we have done so many reactions. Okay. So for oxidation, reaction of alcohol is done. Okay. Next, we'll see the oxidation of aldehyde and ketone. Okay. All these reactions, the reducing agent, oxidizing agent, you must remember they are not going to ask you any mechanism because it's not there. Okay. Just you need to know which one is strong oxidizing agent, which one is weak oxidizing agent. Strong oxidizing agent, we have only 3. What are those? Strong oxidizing agent. KMNO4 with H plus. Then
K2Cr2O7 and CrO3.
Then
K2Cr2O7
with H plus in acidic medium.
CrO3.
And what was the third one?
CrO3.
CrO3. So these 3 you can memorize easily. Strong oxidizing agent. Apart from this, all are weak, mild oxidizing agent. Not weak, mild oxidizing agent. Mild oxidizing agent gives aldehyde from 1 degree alcohol. They won't convert aldehyde into acid further. The strong oxidizing agent, you won't get aldehyde as a final product, but you get acid. Correct? In mild oxidizing agent, PCC, PDC important. Okay. MnO2 very important, which oxidize only allylic and benzylic alcohol. Okay. It does not affect carbon-carbon double bond. That is also very important. Opener oxidation, MPV reduction, these are name reactions. You must remember this. Okay, opener oxidation gives 2 degree alcohol into ketone. What reagent we are using, that also you must keep in. Okay. Next, write down oxidation reaction, the second one. Oxidation of aldehyde and ketone. Write down aldehydes are good oxidizing agent. Sorry, good reducing agent, not oxidizing agent. Aldehydes are good reducing agent. It can be easily oxidized to acid, carboxylic acid. Okay, it can be easily oxidized to carboxylic acid. Ketone comparatively, next line write down. Ketone comparatively is difficult to oxidize. Ketone comparatively is difficult to oxidize. Ketone gets oxidized in very drastic condition. Ketone gets oxidized in drastic condition. Okay. Next line, one note you write down. This property is used to differentiate aldehyde and ketone.
Yes, even in biomolecule, same property.
Yes, that's what.
That was just fructose and glucose, same things.
Right. So what all reagent we use for this purpose? Okay. So the reagent used, the first one you write down.
Bromine water?
Tollens reagent test, and this is what it is: ammonical solution of silver nitrate. Remember, I have told you that we'll do this in the next chapter. It is the ammonical solution of silver nitrate, AgNO3 in NH4OH. Okay. Now you see the reaction of these two. If you see AgNO3 with NH4OH, it gives AgOH plus NH4NO3. NH4NO3. Now this AgOH, when you heat this strongly, if you heat this, it converts into silver oxide, Ag2O, with water eliminates here. And this Ag2O, we have discussed it, this is a mild oxidizing agent. Mild oxidizing agent, and this cannot oxidize ketone. Cannot oxidize ketone. Okay. So if you have aldehyde RC double bond OH with this oxide Ag2O, it converts into acid RCOOH and silver metal comes out. Okay. This silver that is coming out, suppose you have the beaker like this. This is the solution we have of reaction. This silver metal, this sticks to the wall of this beaker like this. It sticks over here. Right. And this appears as a mirror. Silver, when it sticks over here, it looks like a mirror. Right. Hence, this test we call it as silver mirror test.
Yes.
When this looks like a mirror kind of thing, if it appears, it means the reaction is done, and hence it is silver mirror test.
Sir, is this economical to retrieve silver?
What?
Is this economical to retrieve silver?
Retrace silver, you're saying? Retrace.
Yeah.
Economical, not much, but yes, we can retrieve silver from this. We can take silver particles out of this. Okay, economical or not, then we have to see like what kind of process we are using to extract silver from this. But I think it is not very expensive.
Oh, okay.
I'm not very sure with the economical part, but I think it is not very expensive. We can do that.
Okay, sir. Okay. Then we can go sell that silver and all.
Silver is not that costly also.
Oh yeah, I forgot.
So if it depends like what amount you are getting. That is also one factor. No?
Yes, sir.
Copy down this.
Done, sir.
Done, all of you?
1 second, sir.
Yes, sir.
Sir, you didn't tell her over.
What?
1 second, sir. You didn't tell her over.
You pick up questions they just send.
Sorry?
Just send the unit test portions.
This one. I didn't get Advaita, right? Tell me again.
Sir, no, I'm telling the school just sent the unit test portion.
What is the portion?
It's from 29th. Only haloalkanes and haloarenes.
Okay.
Okay, awesome. Slaughter Madi. When
Classes now?
online, sir.
Online. Okay.
8 to 1 school classes are held, sir.
So it's done like what they have done in school. Physical, I think, right?
Organic done. Amines also done. Polymers also done.
I can't finish like this.
Sir?
They are so fast, quick actually.
Sir, like 3 days, 1 chapter done.
So they didn't explain anything.
None of mechanisms they don't explain, sir.
It's not there for both. Anyway, so okay. So tolerance reagent.
How we are doing, sir?
Okay. Tolerance reagent test, since it is mild oxidizing agent, so it is not performed with ketone, and hence we can differentiate this. Okay, aldehyde and ketone. Now, so first of all, what all aldehydes we have which shows this test? Very common and very important question, this one. Right. So write down. The aldehyde which shows this test is few examples I'm writing down. You must memorize this. HC double bond OH. Aldehyde shows this test. No. CS3CHO. Aldehyde again perform this test. PHCHO shows this test. Okay, ketone, if you take this example, this is not possible with ketone. Now this is aldehyde, so you can easily say it shows tolerance reagent test. But we have a compound like this, suppose CS3COH, OR and H. What is this compound?
Secondary alcohol.
Alkyl.
Oh yeah, sorry, I didn't see that. Oh, I didn't see that over.
This is hemiacetal structure.
Ah, yes, sir. Hemiacetal structure. One CO linkage, one OH, anomeric carbon, anomer.
Hemiacetal shows this test. Correct? Why? Because the medium is alkaline. So in alkaline medium, what happens? It takes this H plus, forms H2O, and this negative charge, it comes over here and this goes out. You see, I'll show you the mechanism. The alkaline medium, it takes the acidic hydrogen, forms O minus, HOR plus H2O, correct? Further, what happens when it comes down, this goes out as a leaving group. So it converts into what? Aldehyde. When aldehyde forms, it shows this test. Okay, so aldehyde, hemiacetals shows tolerance reagent test.
One second, sir. So why not other aldehydes?
Aldehydes will show. I'll just give you some example.
Oh, okay. All aldehydes will show.
Aldehyde will show tolerance reagent test. I cannot write all the aldehyde.
Ah, yes, sir, obviously.
OH. This one, it shows or not?
Yes, sir, that
shows or not? For this one, this one,
yes, yes, no, no.
okay.
First two are hemiacetyl because one CO linkage, one COH bond is there. Same thing with second one, not for third and fourth. Is that correct?
First one is hemiacetal.
Yes, sir. One CO and one COH.
Second one is also hemiacetal.
Yes, sir.
This one is
Illa.
acetal structure. It won't show. This one is what?
Sir, nothing, sir.
Why nothing?
It's alcohol and ketone.
In alkaline medium, it goes under tautomerism.
Ketone, enol. Okay, it doesn't matter.
OH, CH double bond, COH, R. Okay, this is one. Again, it goes under tautomerism. This comes over here, and this hydrogen comes over here. So it converts into C double bond OH, single bond CH, OH, R. Aldehyde, hence it shows. Done?
Yes, sir, done.
Okay, so this is the reaction we have for a tolerance reagent test. Okay, this compound you see, this compound we call it as 1-hydroxy 2-ketone. Not the IUPAC thing, but whenever we have keto and hydroxy group present adjacent, it shows tolerance reagent test.
1 second, sir.
Done?
No, sir. Done, sir.
Okay, this is it for today. Okay, next class we'll start with Felling solution test. Okay, write down the heading and let it be. We'll start from Felling next class. Okay,
Which chapter is this now?
this is oxidation reduction reaction.
Okay. I didn't know there was a chapter name.
Yeah, so we are doing all reactions, all kind of oxidation reduction reaction.
Okay, sir.
Okay, chalo, thank you guys.
Thank you, sir.